True or false? If f of x is equal with x in exponent n, where n is an odd integer, then the inverse function exists. First of all, let assume uh, y is equal with f of x. So let's take this in consideration when we are working with the inverse function and when we want to, for example, algebraically to find the inverse function. And now, according to the definition of the odd function, we already know the definition is f of minus x is equal with the minus x. So we already know this definition. And now if we are applying this f of x is equal with y, instead of this x here I can write f of minus x. F of minus x is equal with the minus y, equal with the minus y. And now if we are multiplying everything by the inverse function, f in exponent minus 1 here, we can get f inverse function times the function f of minus x. Already we have here minus x. And this is equal with the inverse function of minus y. Of minus y. And here is minus y. But inverse function times the function is identity function. In identity function we get just the index here minus x. So f, or let me write minus x, is equal with the inverse function of a minus y. So it satisfies this equation, and also the inverse function is odd function, and this function is 1 to 1, so it has the inverse function. It means f of minus 1, f in exponent minus 1, or inverse function of minus y, is equal with minus x. So already we proved this statement here is true. So this is true. So if f of x is if any odd function, if for example f of x is equal with the x in exponent n, when n is odd, then exists the inverse function. This is true. Because it's true, just let me make a little bit more interesting. Let me write here true. So this is true. Now I'm going in the second statement. And the second statement says there exists, I'm sorry, here is there exists no function f such that f is equal with f minus 1. Here we need to find, if we want to prove this, we can go with a counterexample. If we find one example that does not satisfy this statement, then this is not true. So the one good example is, for example, if we have f of x is equal with 1 minus x, 1 minus x, and if we are applying here the rules, if we find here the rules have to find the inverse function. Instead of x here, I can let me apply here simply and shortly. X is equal with 1 minus, instead of the x I can substitute with y, but instead of the y I can go with the inverse function. And I'm taking a little bit of shortcut here just to prove it. And if I'm solving this problem for the inverse function, then inverse function is going to be inverse function of x is going to be equal with 1 minus x. So this case proves here, there exists f, a function that is equal with the inverse function. So, and this is the case. So in this second statement is a false because that exists. And because it's a false, let me write here 1x, and this is false. And for the first statement here, if you want to, for example, graphically to see, I can show here some examples. For example, you see n is a 9, and this is a g is inverse function. And we see visually here, those functions are inverse with each other because it has inverse function because this is symmetric with respect to the line y is equal with x. For example, if I want to find the other odd degree is a 7. You see n in a 7 here, n in a 7. If you want to, for example, in a 5, let me go in 5. The other odd is 5. You see again it has the inverse function. It shows graphically. If you want, for example, to find 3 here, I'm sorry, I need me time 3 again. If you go with 1 is again. And even if you go with the negative integers, so it means even negative integers is going to satisfy. Here is 3. You see is asymmetric with respect to the line. Even if I'm going 5, again the function and the inverse function are asymmetric with respect to the line y is equal with x. So this is we already proved for the first one, for this statement is true, and the second statement is false.